Welcome to this explainer. Okay, if you've ever stepped foot inside a science classroom, you've definitely seen it hanging on the wall, the periodic table of elements. And for a lot of people, let's be honest, it looks like a tedious memorization chart, just this massive, intimidating grid of letters and numbers designed to torture students. But today, we're going to reframe that entirely. The periodic table is actually one of the greatest cheat sheets humanity has ever created. It is a brilliant, predictive map of the universe's building blocks. Understanding this map means understanding the screen you're looking at, the air you're breathing, and the water you're drinking. And the best part, by the end of our time together, you won't need to memorize a single element because you'll understand the hidden logic that governs how they all behave.
Okay, let's dive into this. To avoid any cognitive overload, here's our roadmap for today. First, the ultimate chemical map. Second, coordinates, groups and periods. Third, the atomic tug-of-war. Fourth, understanding periodic trends. And finally, the master key.
Section 1. The ultimate chemical map, covering its history and layout.
So let's look at the actual structure of this thing. Have you ever asked yourself, why is the periodic table shaped like a castle? Like, why isn't it just a simple uniform grid like a calendar or a spreadsheet? Why are there these weird gaps at the top and those two towers on the sides? Well, it turns out that shape is entirely intentional, and it was born out of a really long history of trial and error.
You see, early chemists knew there was a pattern to the elements. Dmitri Mendeleev famously organized his early table by atomic mass, basically just how heavy the atoms were. And honestly, it worked beautifully for the most part, but they kept hitting these annoying little glitches. Take cobalt and nickel, for example. Cobalt is actually slightly heavier than nickel, so if you're going strictly by mass, nickel should come first. But their chemical properties screamed that cobalt belonged before nickel. It was a massive puzzle until a scientist named Henry Moseley made a huge breakthrough. He realized the elements shouldn't be organized by their weight, but by their atomic number, which is the exact number of protons in the nucleus. Suddenly, everything clicked into place. Cobalt has 27 protons, nickel has 28. Problem solved. The modern table was born, organized precisely by proton count.
Moving right along to Section 2, coordinates, groups and periods, and how to read them.
All right, so we've got Moseley's modern map, but how do we actually read it? Well, like any good map, it has an X and a Y axis. First up, we have the vertical columns. These are called groups, and there are 18 of them. You can think of a group kind of like a biological family. Elements in the same vertical column share the exact same number of valence electrons, and those are simply the electrons sitting in the very outermost shell of the atom. Because they have that same outer shell setup, they exhibit incredibly similar chemical behavior and traits. Basically, if you know how the top element in a group reacts, you already have a really good idea of how the one at the very bottom is going to react.
Next, we have the horizontal rows, which are called periods. There are 7 of them. Here's the trick. As you move horizontally from left to right across a period, you're adding protons and electrons, but you are not adding new layers. Each period represents one main energy shell. But the second you drop down to the next row, boom, you add a brand new electron shell. It's exactly like adding a new layer to an onion. So moving across a period gradually changes the properties, while moving down a group physically adds size.
Together, these coordinates create distinct, predictable neighborhoods on our map. Over on the far left, you have the metals. Group 1, the alkali metals, these things are soft, silvery, and so violently reactive, they'll literally explode if you throw them in water. You're never going to find them sitting pure in nature. Group 2, the alkaline earth metals, are also highly reactive. Now, jump all the way over to the right and you hit the nonmetals. Group 17, the halogens. They're highly corrosive, colorful salt formers like chlorine and fluorine. Right next door to them, in Group 18, are the noble gases. They are stable, happy, and completely unreactive. And right in the middle, separating the metals from the nonmetals, is a diagonal staircase of metalloids, like silicon, which have mixed properties and make absolutely fantastic semiconductors.
Which brings us to Section 3, the atomic tug-of-war, the core fight.
So here is the absolutely crucial point. Every single property we just talked about, how reactive an element is, whether it's a metal or a nonmetal, it all boils down to a literal mechanical fight happening inside the atom itself. To understand this fight, we have to calculate what's called the effective nuclear charge. Imagine the positive protons in the center of the atom acting like a giant magnet, trying to pull the outer negative electrons inward. But there's a catch. The inner layers of electrons are in the way, and because negative repels negative, they push those outer electrons away. This is called shielding. Let's look at sodium as a quick example. Sodium has 11 positive protons pulling inward, but it has 10 inner shell electrons pushing outward. 11 minus 10 equals 1. So that outer electron of sodium only feels an effective magnetic pull of 1. It is barely hanging on.
And that dynamic creates the ultimate atomic tug-of-war. On one side, you have the effective nuclear charge, the protons desperately trying to pull those valence electrons inward. On the other side, you have the number of shells, because as you go down the periodic table, you're adding more and more layers, which increases the distance. And just like a real magnet, the further away an electron gets from the nucleus, the weaker that inward pull becomes. This single underlying tension dictates almost everything in chemistry.
The most obvious result of this tug-of-war is the size of the atom, otherwise known as its atomic radius. Now, we can't just easily measure a single atom with a tiny ruler because electrons don't orbit in perfect little circles. They exist in these fuzzy, diffuse clouds of probability. They don't have a hard edge. So chemists use a really clever trick. They take two atoms of the same element that are bonded together, measure the distance between their two solid nuclei, and just slice that number right in half. And that gives us our atomic radius.
Let's move to Section 4, Understanding Periodic Trends and how we can start predicting behaviors.
Let's see how all of this builds our understanding. We can apply this tug-of-war mechanism to actual chemical behaviors, meaning we can predict them without blindly memorizing a textbook. Take a concept called electronegativity. The sources define this informally but perfectly as how badly an atom wants to hog electrons in a covalent bond. Think of a water molecule, H2O. Oxygen and hydrogen are sharing electrons, but oxygen has a much stronger effective nuclear charge, so it acts like a massive electron hog, pulling those shared electrons closer to itself. This gives oxygen a slight negative charge and hydrogen's a slight positive charge, which, by the way, is the exact reason water behaves the way it does.
And this brilliantly illustrates the total extremes of our chemical map. Look at the bottom left of the table, down by francium and cesium. They have a ton of electron shells, making their radius absolutely huge. The outer electron is so far away from the nucleus that it barely feels a pull at all. Because of that, these atoms have very low electronegativity. They actually want to lose that electron. That makes them highly metallic. Now look up at the top right, just before the noble gases. Fluorine is tiny. Its electrons are right up against the nucleus, feeling a massive positive pull. Fluorine is highly electronegative. It is absolutely desperate to gain an electron just to finish its shell.
This whole desire to gain or lose electrons brings us to valency, which is simply an element's combining capacity. If we track valency horizontally across a period, it literally looks like a mountain. Group 1 wants to lose 1 electron. Group 2 wants to lose 2. Skip over the transition metals, and Group 13 wants to lose 3. Group 14, like carbon, is right at the peak. It can share 4. But then, crossing the peak, it becomes easier to gain electrons than to lose them. So Group 15 wants to gain 3. Group 16 wants to gain 2. Group 17 wants to gain 1. And finally, Group 18, the noble gases, are perfectly stable at 0. The combining capacity rises up to 4, then falls right back down to 0.
Finally, Section 5, the master key, bringing it all together into a unified table view.
You now have the underlying logic to unlock the entire table. Let's put it all together. Think of this as your ultimate cheat sheet. Now, what's really fascinating here is that you don't need to memorize any of those trends if you just remember the tug-of-war. Going down a group, you add shells. The atom gets bigger. The outer electrons get further away, so electronegativity goes down and metallic character goes up. Going across a period from left to right, the shell stays the same, but you keep adding protons. The inward pull gets stronger. The atom shrinks. Electronegativity shoots up and metallic character drops. Every single trend on the map aligns perfectly with that one core mechanical concept.
But before we wrap up, I want to leave you with a genuinely fascinating puzzle. Look at hydrogen, the most abundant element in the entire universe. Where would you place it on this perfectly ordered map? I mean, it has one valence electron, so it acts a bit like the group 1 alkali metals, but it's a gas, and it's only one electron away from a full shell, which means it also behaves incredibly like the group 17 halogens. Even today, scientists still debate its true placement, which is a great reminder that while our chemical map is brilliant, nature always keeps a few mysteries up her sleeve.